Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. I'd like to start today's show with a huge shout out for everyone who's taken the time to vote for us in the People's Choice Podcast Awards. It's been awesome to hear from those of you who have left words of encouragement, and we certainly appreciate all the love. If you're a fan of the pod and you've already voted, we'd also like to encourage you to head over to your Apple or Google podcast app or wherever you listen to podcasts and leave us a 5-star rating or review. They are super helpful as we push to grow this show and community. In this episode, I'm joined by Prashant Warier, CEO and co-founder of Qure.ai, a company building AI-powered software for radiology. In our conversation, Prashant and I discussed the company's work building products for interpreting head CT scans and chest X-rays. Prashant shares with us some great insights into some of the things he and his team have learned in bringing a commercial product to market in this space, including the gap between academic research papers and commercially viable software, the challenge of data acquisition and how to best capitalize on what data you do have access to, and much more. We also touch on the application of transfer learning in this space and the algorithms and annotation pipelines Qure has developed to support 3D scans. Let's get to it. All right, everyone. I am on the line with Prashant Warier. Prashant is the CEO of Qure.ai. Prashant, welcome to This Week in Machine Learning and AI.
Great to be here, Sam. Thank you so much for inviting me.
Absolutely. Let's get started by having you tell the audience a little bit about your background and how you got involved in working in ML and AI.
Great. So I have been working in the applied math space for a long time. So my undergraduate degree was in operations research. I got a PhD in operations research, and then started working on. So at that time, this was not part of data science. There's no field like data science when I did my PhD. But after my PhD, which was in operations research, where we were basically optimizing truck routes. So figuring out how shipments should be routed from origin to destination, how we should assign drivers to trucks. And then again, there are lots of rules around how many hours a driver can drive and the duty time that they have. So a lot of, incorporating all those rules to figure out how drivers should be allocated to trucks, assigned to trucks. So those are the kinds of problems that I was solving during my PhD, which were primarily integer programming problems. And so I did a lot of work around optimization then. And then immediately after that, I started working on price optimization and markdown optimization, demand forecasting. I started working for SAP. And so there, we were working on these problems in the retail space, retail and fashion retail space. So this, demand forecasting, some of these problems are very much, they are basically your dependent variable is the sales. And then you have a bunch of independent variables, which are, which again depend upon the kind of product that you're selling. So a fashion product will have very different independent variables than if you look at, for example, products which are retail, typical retail products like a can of milk, for example, or fruits or vegetables, right? So we were sort of worked on that for a while, and then I was in the US at that time, came back to India, and then I set up a company which was called Imagery, which was basically using machine learning to understand customer behavior from cookie data. So we were basically dropping cookies on multiple e-commerce websites and getting a lot of detailed information about how customers are behaving on those websites. So you can actually see how they buy clothing, for example, what products they looked at, what kind of sizes they looked at, what colors they looked at, what styles they looked at, and all of that. Or for example, integrating, for example, what travel sites they went into, how they, where they're traveling to, what travel locations they've looked at, or what kind of movie shows they're watching. So we had a very consolidated set of data from cookies, which we would then utilize to do real-time bidding on ads, on basically online ads. And we had built a real-time bidding platform. And that was then, so that was again, AI driven. I was heading that company, so I was also, playing more of a commercial role in that. And then that got acquired by the organization that I currently work for, called Fractal Analytics. So Fractal Analytics acquired my previous company, and then I joined Fractal as chief data scientist. And in that role, again, as chief data scientist, I was working on some problems, and then we sort of identified there is a large gap in the radiology space where we felt that deep learning could make a substantial impact by automating the interpretation of images. So that's how I sort of transitioned from the chief data scientist role at Fractal into becoming the CEO of Qure.ai, and have been working on building this over the last 2.5 years. And so that's my story.
And Qure is currently in the process of rolling out a kind of a package solution focused on chest radiology. Is that right?
So we have exactly. One of our solutions is in chest radiology, which basically can automatically interpret chest X-rays. And a second solution is on head CT scans, which is basically automatically interpreting head CT scans. Those are the two main solutions we have built. There are some more solutions that we've built over the last several years, but from a commercial perspective, we focus on these two.
And so there's been, over the past few years, there have been a ton of work. In a lot of ways, it feels like a kind of gold rush in the medical field. When you look at the research journals, it's, hey, we've got this new tool, CNN, let's apply it to radiological image type A, type B, type C. There's a series of these types of papers. I'm curious what you've learned about the gap between what you might read in a paper and actually bringing a product to market.
So that's a very good question, Sam. I think I have a very strong point of view on that.
I figured you might.
There are lots of papers, because CNNs, can read images really well, right? And so people felt that, okay, I'll just take a CNN, I'll apply it to this medical data that I have, and I'll get good results. And they do get good results because they're overfitting on the data. So you have 2,000 images. Let's say you have got 2,000 X-rays to train your algorithm on, and you sort of label them. You label each of those images as normal. Let's say these are X-rays, right? You label them as normal or abnormal, and you model on that, and you will get some. You basically put some as validation testing and so on, and you get good results. But what happens is that, especially with X-rays, right, there is a huge variety of data. If you go from a Philips machine to a GE machine, or you go from one center to another, there are difference in settings, difference in machines. There is a wide variation, and what happens typically is you take a data set, you train on that data set, you validate, you test, you do all the right things. But when you take that algorithm and you try to generalize to a new data set, it does not work well at all. And we saw this initially. When we started working on this problem, on the chest X-ray problem, we had around 25,000 scans, 25,000 X-rays, along with their reports. So what we did is we took the reports, we ran NLP on those reports, some rule-based NLPs, not machine learning-based, but rule-based natural language processing, which basically extracted out the abnormality from the report. So if, for example, one of the abnormalities is called pleural effusion, where it's fluid in the lungs. So we said we will extract out a bunch of abnormalities. So we trained the algorithms to do that, to train these NLP algorithms. So now you've got an X-ray and the corresponding abnormality, right? A chest X-ray and a corresponding abnormality. And we trained our models on that. And then what we saw is that when we had a new data set that was trained on 25,000 images, and when we got a new data set, it did not translate at all, the accuracy. We were getting around 90% accuracy on the first data set. On the second data set that we got from another hospital, we were somewhere in the 60s, I think. And so it was substantially lower. And then we figured that there is a lot of variation in the data, and then that's one challenge. And of course, over the last 2.5 years, we have increased our X-ray database from that 25,000 number to around 1.5 plus million. So today we have a huge amount of data. So it sort of has learned a wide variety of data patterns that it sees. Data acquisition patterns, because X-ray acquisition can occur, in many different ways. And so it has learned a lot of these acquisition patterns, learned about a lot of different machines that are generating those X-rays. So that makes it a little bit more generalizable. I think the more amount of data that you have, it becomes more generalized.
You mentioned using NLP to pull information out of reports or records. Is this kind of data mining the electronic medical records to produce labels for your data set? Or was there something else happening?
It's not electronic medical record. So it's basically, you could think of it as a medical record, but basically for every radiology image, you will have a radiology report. are part of radiology information systems.
Ah, okay.
So you are basically just pulling that radiology report. You're not pulling any more medical records. So ideally, a patient will have a lot more. They will have the history of why they came to the hospital,
Right.
why they took the X-ray in the first place, and then maybe there is some microbiological test which gets done afterwards where they are diagnosed with some disease, right? A radiology report may not contain all of that. It will basically tell you that I found these patterns on the X-ray. For example, it might say that I found a pleural effusion, which is basically some fluid in the lungs, or that could be due to a tuberculosis or other disease. But a radiologist will not report on that. They will report on what they see in the X-ray. So it's more visible features.
Okay. These radiology reports, are they coded, or is it just kind of natural text notes from the radiologist?
They are natural text. Sometimes, again, every hospital will have their own format template for reporting. There are some standard templates recommended by the Radiology Society of North America. But again, I think a lot of people don't use those templates. To answer your question, they are very varied, but they have some structure to it.
This question is maybe inspired by a image that you have on the Qure website. It has like you're basically looking at a brain scan on the monitor. I'm wondering if, setting aside machine learning and AI, are we getting to a point where radiologists are looking at these images digitally and creating bounding boxes and like electronically notating these images in a way that will make it easier for future ML and AI applications, or is it still all, manual today?
Absolutely. I think what we are seeing is that definitely there is, a lot of work going in towards creating annotated data sets. And so a lot of hospitals are working on that. I think a lot of the hospitals in the US, for example, a Mass General Hospital, they have their own data science teams, and those teams are also working on similar problems. So there is definitely a lot of effort going towards creating these annotated data sets. So I would not say that, a lot of radiologists are working on it. I think focused groups in different parts of the world are working on these kinds of annotations. And it's not something which is completely standardized yet.
Right. But it sounds like you're also saying that it's not, we're not necessarily seeing the radiologist's tool change to be more like a data annotation exercise. It's happening separately in some data science team that may be, doing similar things to what you were doing.
Exactly, because I'll tell you why, right? So, for example, one of the things we had to do was to when we were trying to detect bleeds from head CT scans, we had to actually go in, or not us, but trained specialists had to go in and mark out the bleed on those scans. And that's a time-taking process because a CT scan of the head will have somewhere between 50 to 100 slices. And for each slice, there will be either some of those slices obviously will not have a bleed. Maybe all of them don't have a bleed, but when you have a bleed, you have to actually mark the boundary of the bleed, which is not a continuous boundary, or it's sort of a ragged boundary, and then you have to mark all of that. That's time consuming for radiologists, and so it will not be easy for somebody to sort of incorporate that into the radiology workflow because they want to see a scan, they want to report on it in a few minutes and then be done with that. And marking out the boundaries will take them maybe 20-30 minutes. So I don't think some of these are easily incorporated into the workflow, which is why we sort of started doing this natural language processing, because we said there is a lot of data already available in the report, because I'm saying that, the radiologist is already writing that there is this pleural effusion in this part of the lung. So we can extract out all that information from those reports and use that for training. So rather than getting them to sort of manually mark out these abnormalities.
So you also mentioned these different acquisition patterns. These are related to the different types of radiology machines?
These are radiology machines. The amount of exposure, amount of radiation that you produce. So there are, everybody will have a different setting. So these machines also have some settings, and so there are many different settings. And so the especially for X-rays, it's the data from each center is sort of slightly different. It's not exactly the same.
Okay, yeah, it's interesting. I think there's a tendency to think about the CNNs or ML and AI in general as these, maybe give them more credit for being naturally generalized than they are. My daughter is doing an internship with the podcast currently where she's taking podcasts that we've already recorded and running them through automated transcription and looking at a bunch of different services and kind of rating their performance. And, over time, we've learned that some of the services do better with, phone calls. Some of them do better with podcasts. Some of them do better with audio that's recorded in a room. Like the characteristics, the very subtle characteristics of the input data have a huge impact on the algorithm's ability to perform well and extract text from them, much more so than you might think. And it sounds
Exactly.
like you've had very similar experiences on the input side with these radiological images.
So I have a very interesting story in this. That's when we started working on chest X-rays, it's probably around 2 years back. So we were sort of still tying up with hospitals. We did not have any hospital data, any real data coming from our collaborators. So we said we will mine the internet for data. So we looked at some internet sources. We collected some 10,000 images, and we said let's try to train a model on this. And we trained a model on that, and that was very accurate. It was super accurate in determining normal from abnormal. So it was classifying normal versus abnormal. And then we said, this is a very small amount of data, right? Typically, if you're looking at images, you're looking at millions of images to train algorithms. And we said, let's see. So we created an attribution algorithm. So we were figuring out if you were to attribute what exactly the algorithm is learning, you can find out boxes. So we can basically, for example, there is something called occlusion-based attribution, where you can black out one small box within the whole image, and then see what is the attribution of that to the prediction. So if you black out a box because of which the algorithm is saying that particular X-ray is abnormal, then suddenly it becomes normal. The prediction changes from normal to abnormal, and you look at how each box is impacting the probability of being normal or abnormal. So the boxes which have the highest impact will have the highest difference between the normal versus abnormal probability when they are blacked out. So we created these attribution methods, and we were trying to attribute the algorithm, what the algorithm was learning, and we found that the algorithm actually was learning to distinguish something very simple, because what was there, these were internet images. So typically all the abnormal images had a lot of text on them, so some typing or some written text, and the normal images did not have any annotation, any kinds of text or anything like that. So it was basically training to recognize typewritten letters. That's what it's pointing to. So if it sees typewritten letters, it will assume that it's abnormal. If it doesn't see typewritten letters, it's normal. So that is what it was learning. And so these algorithms are very, very good. They're very smart, but also they can learn very different things, than what you expect them to learn.
So you've learned the importance of real data and these different input patterns, and you've kind of learned some things about the model's ability to generalize across this. What else have you learned?
The other things that we have learned are also that if you look at when we look at all the research in image. All of them are 224 by 224 images, because that's the ImageNet size, and we look at most research is about that size of image. And if you look at an X-ray, a typical chest X-ray will be around 4,000 by 4,000 pixels. Mm-hmm. So if you are downsizing, so initially when we started out doing research, we started with taking that 4,000 by 4,000 or that size image and downsizing it to downsampling it to 224 by 224, which basically takes away a lot of the detail that you're looking at. So you cannot obviously, if you have a lot of data, it'll learn well. It will be able to detect really large abnormalities. It will not be able to detect subtle abnormalities. And so then we had to devise our own methods to sort of work with higher resolution images. So today we are able to work with full resolution images. So we had to sort of look at patches at a time and do a lot of different techniques. Some of which are our own IP, so we have not published it yet. So I cannot reveal it, but there's a lot of work which we have done, which sort of enables us to look at the full-sized image rather than looking at these downsampled images. And that's all drawbacks of what I see. out there in terms of literature. Everybody is taking these standard sort of dense nets or res nets and then applying them to the downsampled images, and that also loses a lot of information from that original image. So that's, if you look at most of the literature, that's what is happening right now.
Is there anything that you can say generally about the approach that you've taken to look at the larger images? Are you like windowing across the images, or Any hints you can give us?
So it's a patch-based approach. I mean, we look at patches, we determine some patches, so that's all I can say. I mean, I think
Okay.
there is definitely some very very strong IP in there, which sort of because I don't think anybody right now is working on large images. I think everybody else is working on smaller sized images, and we also tried. I mean, so we also tried training these. Larger sized using the typical dense nets, rest nets, and it sort of doesn't perform as well. I mean, or sometimes it doesn't converge at all. So we saw lots of convergence problems with larger sized images. So.
And do you have any intuition for why that is?
I don't actually. I don't. I mean, we have tried that, and I really don't have a clue why that doesn't work typically. I mean, so not sure. But there is not much testing. I mean, honestly, when I look at research, there is not much testing that has been done on larger images because most of the work, I mean, 224 by 224 is a decent size for your regular images. So that's sort of, I don't see that there is a lot of work done in that area.
In your approach and or the literature that you've seen, does transfer learning play a lot? Or are you looking at pre-trained models or models, that are pre-trained with ImageNet or some other data set, or are you just training from scratch?
So we have we found that pre-training with ImageNet and then using that on our data set running. I mean, using pre-training on ImageNet did not improve performance on our data sets. But what we found is that there is opportunity to do transfer learning within the domain. So I could basically learn from other types of X-rays and use that learning to chest X-rays. So there is some of that learning that we have been able to use. But again, that the transfer learning there, the impact of that is very small. I mean, I think it also has to do with the amount of data that we have. Because we have so much data, probably, I mean, the transfer learning is not that impactful. But if you have a amount of data, then maybe if you transfer knowledge from other domains, it might be more useful.
What else have you learned?
I think, some of the learnings are about the annotations also. I mean, so what we have learned is that we can do annotations at multiple levels and train models which can do multi-level. So basically, there are multiple types of classification. So one is to segment out the abnormality. So you're actually, the annotation will involve actually going into that image or that slice of a CT scan and then saying that this is the boundary of the abnormality. So clearly marking that out. A second type of annotation that we have done is looking at, for example, on a CT scan, slice by slice. So you can basically look at one slice and say whether that slice is abnormal or not, which is a much easier task than actually annotating and going out and marking out the abnormality on that. So that's a second type of annotation. And then the third type of annotation is at a scan level, either at the whole CD scan level or at the X-ray level. Using the report, we can extract out the abnormality on that particular scan. So, we have models which combine all three of these. So we have losses, losses which will take the segmentation losses and add the classification losses at a slice level and the classification losses at the scan level and combine all of that. So those are the models where we can actually take all the data that we have, because we have 350,000 head CT scans, and we cannot expect to label all of them. I mean, we cannot expect to sort of 350,000 head CT scans, each with, let's say, 100 slices. So you're talking about 35 million slices. And so we cannot expect to sort of mark out all of them. So you have to mark out a subset of that. And then so we have marked out a subset of that. We have labeled at a slice level a subset of that. And then, of course, for each of those 350,000 scans, we have got reports. So we can extract out the abnormalities from those as well. So we have combined all of this. And then the models that perform the best on our data are ones which combine all the knowledge from all of these types of annotation.
So just to clarify then, if you're, when I think about a traditional, like a ResNet type of a model, that's a model that is basically looking at a single image. Is the implication that you've built out an architecture that, is almost, I'm almost thinking of it like a 3D type of architecture that takes in multiple slices and kind of understands the relationship between these slices relative to the whole scan?
Right. Exactly.
Tell me a little bit about the process of defining or coming up with this model architecture. How did you arrive at the final architecture for doing that?
So I think, it's primarily trial and error. Reading the latest papers, and we have, around 10 plus deep learning scientists now. Each person focused on their own problem. And I think what we have basically been doing is, looking at what is the latest research in a specific space and trying to implement that. So we implemented many different techniques from many different papers. Some of them work, some of them don't work, or a lot of them don't work. Very few of them work, but so a lot of them don't translate directly. I think what we have seen is that there are lots of new techniques out there, lots of new, which show very promising results on the paper itself shows very promising results. But then when we apply it to the domain that we are working in, it doesn't really translate well. So we have seen that. Typically our architectures are very simple. In fact, what we have found is that the simpler you make it, the better it is.
Can you give me an example of something that you tried that was, more on the complex side that you thought would add a lot of value, but it ended up doing something simpler, worked out better?
We were trying GANs at some point of time to see if we could generate abnormal and normal X-rays using GANs, and then use that for training or use that to do data augmentation. And we have tried other techniques. Some of the techniques from video action recognition in videos we've tried for our head CT scan technology, and some of these, some of these have not really worked out. I think more complex technology we have not seen that it sort of translates to real. I would not say that some of the technologies that we developed have not been complex, but again, I think in general, I'd say that a lot of things that we've tried have not worked out.
Yeah, it sounds like you're describing a world in which we might think of as applied ML and AI. There's still a lot of research involved in your process for developing this product suite and bringing it to market.
Absolutely. I think there is a huge amount of research. There is a huge amount of domain knowledge which we have brought in. Which just makes the algorithm much better. So, simple things actually make it easier. So for example, if you're detecting fractures, if you if you just train a model on fractures, you'll probably see a lower accuracy. But if you look at what is around the fracture, if you also detect bleeds and use that to improve your knowledge about the situation, we get a better accuracy, better probability. So, if you have a fracture, you most likely have a bleed in the brain also. So I think bringing in a lot of domain knowledge is critical in some of the areas that we're working on. For example, detecting tuberculosis, you have to look at certain types of features. So you have looking at certain things, on the upper lungs. So if it's in the lower part of the lungs, that's not going to be very relevant. So we have, brought in a huge amount of radiology knowledge into the algorithms we have developed, and those actually add a lot of value. And of course, the research also is there. We also have to do a lot of research because, as I mentioned earlier, most of the material out there is focused on the types of images that are much smaller and also two-dimensional, right? So you're looking at mostly two-dimensional videos, two-dimensional images. Only in case of videos, you're looking at something which is not two-dimensional, but at least your sequence of images. And we look at a CT scan or MRI. All of these are three-dimensional images. So you have to sort of get knowledge from all of the slices and bring that all together to infer a classification there. So we have to sort of ingest knowledge from these sources, which again, there is not much literature out there on some of these topics. So though of course, there are lots of people now working on technologies in the medical space. But when we started, we started around 2.5 years back. There were very few people who were working on deep learning in the healthcare space, which has exponentially increased in the last couple of years.
And out of curiosity, have you directly applied any of the work or models that originated in looking at videos to this CT scan problem?
We have.
Did that work out, or was that another dead end? Or
I think that's something that has worked out for us. Some of these techniques have worked out for us, but I would not be able to go into much detail on that right now because it's still something that we are working on, and we don't have. So we have not published anything on that yet.
The company has been active in publishing some of its research findings. What are some of the recent work that you've published?
So we have published, recently we published our work on the head CT algorithm, which basically detects multiple kinds of bleeds, fractures, midline shift mass effect from from head CT scans. And this we sort of published some details of the algorithm. This is the earlier version of our algorithm, which is probably around around a year old. And we sort of did a validation study of that on a data set where, so we had a data set of 350,000, of which we had basically a training set, a validation set, and a testing set. But then what we did is we went out and collected an additional 500 scans, which was from a very different source, completely new source. And we had those three sort of reported, or basically a radiologist had to go in and mark out on a user interface whether they found a intraparenchymal bleed, whether they found a fracture, and so on. So this is just a tick box. And we had sort of three radiologists do that on those 500 scans. And we also compared our accuracy against that. And we found that we were 95%, 0.95 plus AUC on all of these, detecting all of these abnormalities. Now this is slightly older. So the technology that we have published there is maybe around a year old. Now it is currently, what we are looking at is around 0.97, close to 0.97 plus on all abnormalities. So it's improved a little bit since we published that work.
Have you published any data sets in this space?
Yes, so we also open source this data set of 500 scans. It's actually exactly 491. We have published that, we open source that data set along with the ground truth for that, which is basically the reading of three radiologists. One of the challenges that we found is that everybody claims their own accuracy, and there is no common data set on which people can sort of compare their accuracies. Like, for example, ImageNet is there; you can compare accuracies on ImageNet. Right? There is nothing in in most of these spaces. So head CT, we said let's put together this data set, and then we published our results from that. Of course, we anticipate that other people can also use that to publish their results on that particular data set.
And you said how many scans in the data set?
491.
And is that number of scans enough to really build interesting models against?
It will be hard to get a very accurate model. You could start and you could build some models on that. It definitely, you could build models. Maybe the accuracy will suffer a little bit because it's not very large. So basically, we have 491, of which I would say around 300 or so. I don't remember the exact numbers, but around 300 of them are abnormal. And of those abnormalities, if you look at a specific kind of bleed, let's say an extradural bleed, there are probably around 40-50 scans which have got extradural bleeds. So that itself may not be enough for you to determine and be able to train a model to identify an extradural bleed. But this data set, the intention was not for people to train, more for people to validate. So you can get and measure your algorithm, which you've trained on another data set, and you can measure your performance on this data set, and you can definitely measure that to a very high level of accuracy.
Okay.
So it's more of a testing data set.
Got it. And are the scans these full three-dimensional scans with multiple slices each as well, or are they static slices?
They are three-dimensional, so they have, I would say, anywhere from 50 to 100 slices per scan.
What kind of uptake have you seen on that? Have you seen other groups doing validation against it and publishing their results?
I have not seen, at least I have not looked at it in the last month or so, but before that I have not seen. We released this data set in March, so it's not been a long time. But we have seen, so I don't know if other people have published. I have not seen anybody publish against it as far as I know. But we have seen, hundreds of people download that data. And so hopefully we'll see some publications out of that soon enough.
When you're building out these models, so you've looked at head CT scans, you've looked at chest x-rays, you've looked at skull fractures. Is your objective to create a single model that is able to detect abnormalities, in each of these different, very different scenarios, or are you building a suite of very specialized tools that is, specially trained and focused on one particular problem space?
It's much more. Actually, we are building very, very specialized tools. In fact, if you look at chest X-ray, we detect 15 different types of abnormalities. And for each abnormality, we have multiple models. And so it's an ensemble of many models. So the number of models that go into even detecting these abnormalities from a single chest X-ray, on a single chest X-ray, we run around 112 models right now to determine all the different things we can report on that X-ray. So we are building very, very specialized models, and I don't think we will not definitely. I do not anticipate that we will be building models which can detect multiple kinds of abnormalities from different kinds of images. So we'll have very specialized algorithms for each.
When you take a step back and you think about bringing these types of tools to market, what are some of the things that you've done with this in mind to build, I want to say build scale, but that's not really the right word. It's almost like manage technical debt to, manage all of these models and to allow you to efficiently manage all of these models, I guess, and bring them to market? Or is there tooling that you've built or an approach that you've taken that helps you manage all of the complexity created by having so many very specific models?
I mean, I would also add there is one more complexity is that these models are improving at a very, very fast rate. I mean, so every month our models improve by a few percentage points. So that is also there. I mean, so in terms of a release cycle for our algorithms, we also have to figure that out. So there are multiple challenges, but what we are one of the things that we are doing is to deploy these models as a cloud-based service. So that is the preferred model of deployment for us. So in that cloud-based service, then you can sort of you're basically you can host those models and you have full ownership of the models. And if you want to sort of upgrade them, it's not too much of an effort because you are owning that. So that's sort of the model that we prefer in terms of deployment. Of course, I mean some places we are working towards an on-premise deployment, and then in those scenarios, upgrading the models. I mean, they get a static version. I mean, they get a current version, and then upgrading them will be challenging. So cloud-based service allows us to mitigate some of the problems that you talk about.
Prashant, thanks so much for taking the time to chat with me. This has been super interesting, and I've enjoyed, learning from what you've learned.
Thank you so much, Sam. Great talking to you as well. And thank you for inviting me on this podcast. Great talking to you.
Fantastic. Thank you. All right, everyone. That's our show for today. For more information on Prashant or any of the topics covered in this episode, head over to TWiMLAI.com/talk/165. Don't forget to visit TWiMLAI.com/nominate and cast your vote for us in the People's Choice Podcast Awards. As always, thanks so much for listening, and catch you next time.